Today we discuss an important idea about matrices called the rank, and we begin with the definition. It says the rank of a matrix A, denoted rank A, is defined as the number of leading ones in its reduced row echelon form. So if you have a matrix and you get its reduced row echelon form, let's begin with this example, an easy example. Suppose we have this matrix. This matrix is already in reduced row echelon form. And we are saying that the rank of a matrix is the number of leading ones in its reduced row echelon form. So where are the leading ones? This one, that one, that one. And remember that when you have the reduced row echelon form, every row has at most one leading one, and every column has at most one leading one. So immediately we can deduce one fact about the rank of a matrix, that the rank cannot be greater than the number of rows, right? The number of rows, um, the rank of a matrix cannot be greater than the number of rows because every row has at most one leading one. And you could even have a situation where a row does not have a leading one. So imagine a situation like this, where this second row does not have a leading one. So the rank of this matrix, because there's only one leading one, the rank of this matrix is 1. I should have said that the rank of this matrix is 3. So the rank of a matrix cannot be greater than the number of rows. Uh, Similarly, the rank of a matrix cannot be greater than the number of columns. For the same reason, because a column has at most one leading one. Here, this column has a leading one, but all the remaining columns do not have leading ones. And so the rank of this matrix is 1. And even though the number of columns is 4, the rank is only 1. So again, the fact holds. We are going to deduce more facts about the rank of a matrix, but for now, let's do some examples. So here we want to find the rank of the matrix given below. This is the famous 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix. How do we find the rank? Well, recall the definition. The rank is the number of leading ones in its reduced row echelon form. So we want to put this matrix in reduced row echelon form. We begin with elimination. So let's say we subtract the first row, a multiple of the first row from the second and the third. So we subtract 4 times the first row from the second row and 7 times the first row from the second row. We can do that. We can also do another thing, which is instead of subtracting the first row from the second and third rows, we can subtract the second row from the third row. That's also a permissible operation. So let's see. Let's say we write 1, 2, 3. That's the first row, doesn't change. We subtract the first row from the second. So we have 4 minus 1, that's 3. 5 minus 2, that's 3. 6 minus 3, that's 3. So this one, we got it by saying R2 minus R1. Now we want to do, instead of doing R3 minus some multiple of R1, we want to do R3 minus R2. Let's see what that gives us. That gives us 7 minus 4, that's 3. Then we have 8 minus 5, that's also 3. And then 9 minus 6, that's another 3. So this is sort of a clever way of going about it. I know it's not necessarily obvious, so we can do it the traditional way. Maybe we'll try that also and see if that gives us the same result. But from here, we can see that we can subtract the second row from the third row, and we're going to get a row of zeros. And that's convenient. And then we can also subtract the first row from the second. So we have R2 minus R1, and then we have R3 minus R2. And what does that give us? We have 1, 2, 3. Then subtracting the first row from the second, we have 2. That's 3 minus 1. Then 3 minus 2, that's 1. And then 3 minus 3, that's 0. And then here, we subtract the second from the third. So we have a row of zeros. Now, what we want to do, we want to subtract. Oh, I should have subtracted 3 times the first row. So, well, that was my mistake, but no problem. We can do it again. I should have subtracted 3 times the first row from the second, but it doesn't matter. This is row reduction, so we can do it in whatever way we want. So let's subtract. We have 1, 2, 3. We subtract twice, 2 times the first row from the second, so that gives us a 0 here. Then we have 1 minus 4, that's minus 3. And then we have 0 minus 3 times 2, so we have minus 6. And then we have 0, 0, 0. So here, what do? We subtracted twice the first row from the second, so R2 minus 2R1. That's what we did. And that gives us this result. Now, one thing we should have mentioned when we presented the definition of the rank is that, yes, the rank is the number of leading ones in its reduced row echelon form. But this is actually equivalent to saying is the number of leading entries in any row echelon form. So at this point, we could actually stop and say that we have this leading entry, in this case a leading one, and we have this leading entry as well, which is not a leading one, but a leading minus 3. But just to conform with the definition, we can continue by dividing the second row by minus 3. So we get the first row remains unchanged, 1, 2, 3. And then we have here 0, 1, 2, because we divide the second row by minus 3, and then we still have our row of zeros. So that gives us the row echelon form. We can continue to get the reduced row echelon form, but that's not going to change anything. It's not going to change the rank, but let's do it and see. So from here, what do we have? We want to use 1, this 1, to eliminate the 2. So what do? We subtract 2 times the second row from the first. So let's write, we subtract 2 times row 2 from row 1. And what will that give us? Well, we have 1, then here we have 0, then here we have 3 minus 4, that's minus 1. And then here we have 0, 1, 2, then 0, 0, 0. So this is what we get for the reduced row echelon form. And so now we can count the leading ones. There are 2 leading ones. That means that the rank of this matrix is 2. I know we didn't use a very direct method to get to do the row reduction, but it doesn't matter how you do the row reduction. You're going to end up with the same reduced row echelon form, and the number of leading ones is going to be the same, so the rank doesn't change. Let's look at another example. So here, we want to find the rank of this matrix. This is a 4 by 3 matrix. If we recall, we know that the rank cannot be greater than the number of rows, and it cannot be greater than the number of columns. So even before we do anything, we know that the rank of this matrix is less than or equal to 3. Now let's see what we actually get. So here we do row reduction. We can subtract row 1 from everything. Subtract row 1 from every other row. And what does that give us? Well, row 1 remains the same, 1, 2, 1. When we subtract it from row 2, so let's see, row 2 minus row 1, we'll do row 3 minus row 1, and then we'll do row 4. We'll do row 4 also minus row 1. Row 4 minus row 1. So subtracting, we get 0, 0, 2. Subtract again, 0, 0, 3. Subtract. Here we can subtract 2 times row 1 from row 4. So row 4, we won't do row 4 minus row 1. We'll do row 4 minus 2 times row 1. So that gives us 0, minus 1, 2. All right. So what do we do next? Well, we want a leading one in the second column. So we have a leading one in the first column. Would have liked this position especially to have a leading one, but it doesn't. But then we notice that this one does. So we can swap these two rows. So let's go ahead and do that. Go ahead and swap those two rows. While swapping also, we'll multiply that row, the last row, by minus 1 so that we have a 1. So 1, 2, 1. Then 0, 1 minus 2. Then we can maintain the other rows, 0, 0, 2, 0, 0, 3. So here, what have we done? We've interchanged this. We interchanged rows. Okay, so we actually did more than one interchange, but essentially we brought row 4 to row 2, and then we moved row 2 to row 3, and then we moved row 3 to row 4. So that's a whole bunch of operations. If we wanted to write them down, we could write something like row 4. So row 4, we multiplied it. The first thing, let me bring the arrow down. The first thing we did was to multiply row 4 by minus 1. So minus 1 times row 4 was moved to row 2. And then we moved row 2 to row 3. And then we moved row 3 to row 4. All right. So we can continue with our operations. We have a leading one here. That's nice. We have another one here. We would like another one here. So what we do is we divide that row by 2 so that we get a 1 there. So let's do that. We divide row 3 by 2. What does that give us? Here we have 1, 2, 1. Now, even before we do that, I should point out that at this stage, we can deduce the rank because we have somewhat of a row echelon form. We can see that we can get rid of the fourth row. We can get a row of zeros by using a multiple of row 3. But let's just stick with the rules and see the rules of getting the row echelon form and see what we get. So here we divide through row 3 by 2. So we have half of row 3, and then we have 0, 0. Here, after doing half of row 3, we can subtract 3 times of that from the last row, but let's just finish this step, and then in the next step we'll subtract 3 times row 3 from row 4. So we have row 4 minus 3 times row 3. So we have 1, 2, 1, 0, 1, minus 2, 0, 0, 1, 0, 0, 0. So this is a row echelon form. If we want to get a reduced row echelon form, then we have a bit more work to do. And that would be, we have to use this one to get rid of this 2. And then we have to use this one to get rid of everything above. Let's do that, even though we don't really have to, because at this stage, we already have our leading ones. Even though this is not the reduced row echelon form, we have our leading one. So we know that the rank of this matrix is going to be equal to 3. But just for the sake of completeness, let's go ahead and get the reduced row echelon form. So we subtract 2 times row 2 from row 1. So row 1 minus 2 row 2. Let's see what that gives us. We have 1, then we have 0, then we have 1 minus 4. So that's 5. Then we have 0, 1. We can use row 3. We can use row 3 to get rid of this minus 2. So we add 2 times row 3 to row 2. So row 2 plus 2 times row 3. So that'll give us a 0 here. And then we have 0, 0, 1, and 0, 0, 0. Then we can go further. Subtract 5 times row 3. So row 1 minus 5 times row 3. That gives us 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. So this is the reduced row echelon form. And the number of leading ones is 1, 2, 3. So the rank is 3, as we deduced even at this stage. So this is the kind of process you have to go through to find the rank of a matrix. All right, let's go ahead. So there's a relationship between the rank of a matrix and the number of solutions of a linear system for which it is a coefficient matrix. So when you have a system of linear equations like this one, x plus y plus z equals something, let's say 0, x minus y minus z equals something, let's say 1, x plus y minus z equals something, let's say 2, then you can write the augmented matrix as 1, 1, 1. Then you have the 0 here, that's for this one. Then you have 1 minus 1 minus 1. Then you have 1, that's for this one. Then you have 1, 1 minus 1, 2. So these guys on the right are the constant terms here. And then this one is what we call the coefficient matrix. Now, the rank of the coefficient matrix tells us a lot about how many solutions a system of equations will have. And that's what we want to look at with these examples. So here we're asking, how many solutions does each system have? Now, in this system, we have, in the first system, we have this row at the bottom, 0, 0, 0, 1. What does this mean? This means that 0x plus 0y plus 0z equals 1. Now 0x plus 0y plus 0z is always 0. So we have 0 equals 1. Now how can that be that 0 equals 1? So in this case, we have an inconsistent system. So let me write it, an inconsistent. We have an inconsistent system because we just cannot resolve this situation of 0 equals 1. Now let's look at this second system. Here we have a whole row of zeros. And what does that give us? Again, it gives us 0x plus 0y plus 0z equals this time 0. So here we have a 0 equals 0 situation. And what that means is normally that would mean that we do have a situation of infinitely many solutions, because we do have at least one free variable in this case. Here we have a leading one here, a leading one here, but this column gives us a free variable. That means that from this last equation, we can write, for instance, z equals 4. After writing the z equals 4, what we have is x plus 2y plus 0z equals 4. But we can set y equal to a parameter. Sorry. We can set y equals a parameter. And when we do that, then in the first one, we have, in the first equation, we have x plus 2y will now be 2t plus 0 is equal to 4. So we have x equals 4 minus 2t. We've already found y to be t, set it to a parameter, and then we found z to be equal to 4. So the set of solutions for the system is going to be 4 minus 2t, then t, then 4. So for every value of t, we're going to get a different solution. Every value of t is going to give us a solution. So we have an infinite amount of solutions here. So here we have infinitely many solutions. Infinitely many solutions. Now let's look at the third one. In the third one, what do we have here? We have that z equals 3. And then from here, we have that y equals 2. And from here, we have that x equals 1. So because it's in reduced row echelon form, it's very easy to find the solutions. And we have a unique solution. Unique solution. All right. So again, I said this gives us an idea of the relationship between the rank of the coefficient matrix and the number of solutions that a system that's based on it has. So let's see if we can discuss these facts further. The first is that, okay, so let's begin formally. Consider a system of n linear equations with m variables, that's m unknowns, which has a coefficient matrix A of size n by m. We want to show that the inequalities, the rank of A is less than or equal to n, and the rank of A is less than or equal to m hold. We already discussed this inequality, but let's just look at it again. So here we are saying that the rank of the coefficient matrix is less than or equal to the number of rows of that matrix, and it's also less than or equal to the number of columns of that matrix. Let's look at that. So here, because we define the rank as the number of leading ones in its reduced row echelon form, and every row has at most one leading one, and every column also has at most one leading one, we automatically have these two inequalities, that the rank cannot be greater than the number of rows, and it cannot be greater than the number of columns. So that's how we prove this one. Now, the second is that if the system is inconsistent, then the rank of A, that's the coefficient matrix, is less than n. And here, n is the number of equations or the number of rows if the system is inconsistent. So let's go and look at the examples we just looked at and find what happens in an inconsistent system. So we had the inconsistent system over here. And what we see here about the coefficient matrix. To have an inconsistent system, you need a row that has the form 0, 0, 0, and then eventually a 1. Now, when you have this, what does this say about the coefficient matrix? It says that the coefficient matrix that's just the side has a row that is full of zeros. Now, if it has a row that's full of zeros, it means that that row does not have a leading one. And the rank is the number of leading ones. So if you have a row that cannot have a leading one, then you're going to be rank deficient when it comes to the number of rows. So your rank is going to be less than the number of rows. So that's what this is telling us, that if the system is inconsistent, then the rank is going to be less than the number of rows or the number of equations that you have. All right, the third one says if the system has exactly one solution, then the rank is equal to the number of columns. Now let's go and look at um, the situation where we had exactly one solution. So when we had exactly one solution, that was this one, a unique solution. He's saying that for that to happen, you need, it says that when that happens, when the system has a unique solution, then you have the rank being equal to the number of columns. Yes, that is true. When we had a unique solution, our rank, which was equal to 3, was equal to the number of columns. But let's look at why that would be the case. If the system has exactly one solution, then the rank of A, that's the coefficient matrix, is equal to M. Now, recall that every row has at most one leading one, and every column also has at most one leading one. Now, when you have a unique solution, you have this situation where the every every column has a leading one. That's what it means. Because if you don't have a leading one in a column, you end up with a free variable. And when you have a free variable, like in this second situation, when you have a free variable, then that's where you're able to set it to a parameter. And then for every value of that parameter, you get a different, or you get a solution, a different solution. You have many different solutions. So to have a unique solution, you need every column to have a leading one. And with that leading one, you're going to get your unique solution. So that's where we can deduce this fact from. The fourth one says if the system has infinitely many solutions, then the rank of A is less than M. So let's look at our example where we had infinitely many solutions. That was this one. In this case, the rank of A must be less than the number of columns. Yes, again, this springs from the fact that we're going to have a free variable. When you have infinitely many solutions, you need to have at least one free variable. And to have a free variable means that in the column where that variable was supposed to be leading, you don't have a leading one. And so you're going to be deficient in terms of the number of columns. You're going to have more columns than you have leading variables. So your rank is going to be less than the number of columns. So that's what this one is telling us. So these are a few facts about the rank of a matrix and how it relates to the number of solutions that a system of linear equations that has it as a coefficient is going to have. See you later.